I'm Angshuman Modak. So I'm a faculty at the Climate Studies, interdisciplinary program in Climate Studies at IIT Bombay. So I work on any problem related to climate change. So you force the system responds, and that is what I work on. So today's topic, today's title, I was really, it took me some time to decide what title it should be, because I thought I'll give you a very a brief introduction on climate change. Basically, it becomes slightly misleading when I hear few things from different people about climate change. So I will try to clarify those things. So the title of today's talk or maybe lecture is climate change, climate system. I'll talk a bit about the energy balance, which is a very important thing. Little bit about climate models, from simple climate models, how it has grown to current, the GCMs and then ESMs, the Earth system models, the global circulation models, global climate models, then climate feedbacks and climate sensitivity. So let's begin. Yeah. So before that, I hope all of you know the difference between weather and climate. So weather is something that you get. So let's say you want to go to Cherrapunji. You expect that in Cherrapunji it will be raining because you love rain. You go to Cherrapunji, but the day you land there, you see it is sunny. So that particular is the difference between weather and climate. So from IPCC, they have defined in this way. Weather describes the condition of the atmosphere at a certain place and time with reference to temperature, pressure, humidity, wind, and other key parameters. But mainly these are the key parameters. And the presence of clouds, precipitation, occurrence of spatial phenomena such as thunderstorm, they define weather. And what is climate then? Climate is basically the average of weather. Typically, the period of averaging is 30 years. But many a times you will think, why 30 years? So there is no general, so at present, even 10 years averaging is also sometimes considered as climate. But from WMO, like long back, it has been decided that a 30-year average is called as climate. And what do you average? These parameters that I was talking about, the key elements of meteorology. So again, so climate is what you expect and weather is what actually happens, what you get. So now coming to the climate system. So in 1992, UNFCCC, United Nations Framework Convention on Climate Change, defined the climate system as the totality of the atmosphere, hydrosphere, biosphere, and geosphere and their interaction. So this is climate system. So when you talk about climate change, you have to know any of these components of this climate system. If there is a change because of some perturbation, which the perturbation could come from anything, from any external forcings. So that particular response is what we understand as climate change. But anyway, so we can start like this: climate system, a black box. And then you have the components, the atmosphere, which has gases, aerosols, and other things. The hydrosphere, which constitutes which has the oceans, seas, rivers, lakes, underground water. Cryosphere, sea ice, lake ice, river ice, snow cover, glaciers, ice sheets. The lithosphere, which is the land, the solid, the upper mantle of Earth's crust, and sea ocean beds, and the biosphere, which is again very important. So only recently people have started working a lot on developing models for biosphere and integrating it to the GCMs. So they call it the Earth system models. So now, so and they look like this. It looks like this. So again, I have taken this from IPCC, the latest report, AR6. So you can see they have different. It consists of aerosols, clouds, ozone, which is an important, greenhouse gas, as well as it's a very important gas which basically blocks the UV radiation from sun. The greenhouse gases, again, large aerosols, but you can consider them to be aerosols. And then the natural fluctuations in the sun, which causes So the sun is the primary source of energy and life in Earth, right? So the whole of this is basically the climate system. And now when you perturb this system, how do you perturb? Let's say you change the amount of aerosol in the atmosphere. Let's say you make a lot of cement to make buildings, and you are emitting a lot of aerosols in the atmosphere. So that basically changes the system, the atmosphere, that component. And now, so what are the forcings? So the external forcings, of course, it is the sun, the solar cycle you have, and the volcanic eruptions, that is also considered to be an external forcing, and we humans. So what we do, that's why we are talking about this anthropogenic forcing and all. And when you force the system, as I was saying, the system responds. And this response of the system, when you consider a long period, let's say 10 years or more, you call that as the climate is responding, the climate is changing. In all this, the key thing is that the key point is that when we perturb any of the components of the climate system, we ultimately affect the planetary energy budget. So it all starts from the planetary energy budget, the energy balance of our planet, when we talk about climate change, when we talk about climate change. I'll stop there. So let's go ahead. So we will come back to energy balance of our planet. But before going there, I want to show you, I have taken again this from most of this kind of illustrations I have taken from AR6 to give you the latest information. So you see here, it shows the climate system, right? And here they have very nicely shown how CO2 concentration has changed since 1850. So 1850 is a very key year, we call it as pre-industrial because very less amount of, there were no, major emissions of greenhouse gases or aerosols in the atmosphere. So basically 1850 to 1900 is considered to be a, the reference period for calculating all the changes in the climate, or the components of the climate, or the variables, or the elements of the climate system. So now here it shows the precipitation changes over time. So you can see here they have nicely separated out the northern hemisphere and the southern hemisphere. You can see that it has gradually increased, right? The precipitation is increasing in the northern hemisphere. So you must think now why it is increasing, why it has increased. And again, there are extreme precipitation events also, whether they have increased or not. So they all come under this climate change issue. So the glacier mass has also lost because of the warming. And you can see the global surface temperature here. So it was always blue stripes in the beginning. So blue is colder, and see how fast it has increased. So what is the present global mean warming change? What is the present climate change compared to, let's say, the pre-industrial period? Do anyone knows that number? What? 1.5 was the target that we wanted to, stop ourselves, but we cannot achieve that. We are closing to 1.5, so it is something around 1.2, 1 to 1.2. 1.2, it is what is reported in the AR6 report. So other than these two, the global sea level is rising, and Mumbai, from where I'm coming, is a coastal region, so we have to be worried about that. And the ocean heat content, it's a very important thing because the sea level rise is primarily governed by the amount of heat content the ocean takes up, or the ocean has. So how dramatically it has increased, you can see it is very dark blue, and now it is, like maroon. It is not even red, brownish. and here, this is the iconic, like the evolution of global mean surface temperature over time. Again, the base period is 1850 to 1900. By the way, in the previous one, different variables have different, base periods. And the other thing is that all of these are from the observations. No modeling, nothing has been used, okay? So the CO2 concentration, long back, they have used the ice cores to get the CO2 concentration. Okay, so a lot of proxy data has been used to reconstruct to get the numbers in the early period of this historical period. So here it shows you again the observed global mean surface temperature change, how it has increased. Of course, the base period is 1850 to 1900, so it is hovering around zero. But you can see what they have done. They have averaged different periods, and they have shown that how it is increasing. So again, coming back to the planetary energy budget, a little bit of history. So Fourier was the first person who formulated this idea of what determines Earth's temperature, and he developed the idea of planetary energy balance. So this is the same Fourier who gave Fourier analysis. Okay. So see, he has been also thinking about climate and climate system and Earth and all. And the next person who is like a kind of, you can say, a pioneer in climate change. I mean, how he told almost more than 100 years back that if you increase carbon dioxide, which is a greenhouse gas, that will warm the planet. And it was, you can see, I mean, 1896. So I have also, I got this paper as well to show you what he has done. Of course, he has written in Swedish. They have translated it to English. And see, the title of the paper was on the influence of carbonic acid in air upon the temperature of ground. Because that time he did not have the idea of surface temperature, because there are different definitions of temperature on the surface or skin or 2-meter temperature. So for him, it was temperature of the ground. He was worried about that. And he said that if you double the amount of carbon dioxide in the atmosphere, the temperature rise would be something around 5 to 6 Kelvin. And I'll show you probably in the end of this talk that he was not bad, even though he was like more than 100 years back, he has predicted this. So now I'll show you the present energy budget. So this red box shows you the top of the atmosphere balance. So 340 watt per meter square comes from sun. About 53 gets reflected back, and the amount of thermal outgoing radiation because of Earth's temperature is something around 267 watt per meter square. But do you think something is missing here? So all these arrows, all these shades, the yellow one shows the short wave, and this one shows the long wave. This is the surface fluxes, but something is missing here, right? Clouds, right? So what happens when you have clouds? So this is the all sky picture. So when you have all sky picture, you see the reflected, which we call as the planetary albedo, the albedo of the planet. It is about 100 watt per meter square, and this is 340. So now they are in balance, right? 340, 100 and 239. So 1 watt per meter square, there is imbalance. And where that imbalance is going, can you tell? It is there in this energy flow diagram. Please look at it. Yeah, greenhouse effect is causing that. I'm saying this difference, 340 minus 100 is 240, but the amount of energy that is going out in long wave is 239. Where this difference is coming? What? No, the answer is here. Please look at the good. So see here, this was a major challenge, in this IPCC, because they wanted to really quantify this number and present it in front of people. Although the policy people, the politicians, they don't understand, but for the scientists, this number was important. So see this, they have given this number now. So where it is going, the imbalance is going, it is taken up by the ocean, and that's why the ocean is heating up. So there are different other absorption. For example, the atmosphere absorbs almost 80 watt per meter square. So these are the details. You can look at it, and we will come back to some of this when we will work on the simple models. So now, because planetary energy budget, we have to know a bit about the Stephen-Boltzmann law. I'll just, this particular relationship is important, so I'm introducing it here. So the black body flux density or the irradiance obtained by integrating Planck's function, which looks like this. For different temperature, a black body will have this kind of function. So if you integrate this, you will get something like this: EB equal to sigma T to the power 4. Okay, and Planck's function was basically which led to the development of theory of quantum physics. And if you want to get into the details, it looks something like this, the expression. It was derived by Planck. So we will use this heavily now to work on the simple models. By the way, what is the current temperature of Earth? Not the temperature change, which we already know now, 1.2 Kelvin, but what is the temperature of Earth now? What? 17 what? Okay. Any other guesses? Someone said 23. 23 what? Kelvin? Please tell me what is the surface temperature of Earth? So it is 288 Kelvin, 15 degree. But now if you consider this 1.2 degrees, so it is something around 16 degrees centigrade or 289 Kelvin. Okay. So now having a 289 Kelvin temperature, and if you consider Earth to be a black body, where the Planck's function for Earth will be? Can you tell me where it will lie in the graph? Yeah, just guess. It is fine. I mean, it will bring new avenues. Yeah. So it will be here somewhere, maybe in this blackboard or somewhere here. Okay. So now coming back to energy balance. So this balance I have done when the system is in equilibrium. Okay. So as Ashwin was telling yesterday, that C dt by dt is equal to R in minus R out, something like that. So the C dt by dt presently, let's say, is 0. It is in equilibrium. So the R in the radiation incident minus reflected back radiation is balanced by the radiation emitted by Earth because of its temperature, right? Let's say you consider Earth to be a black body and it is emitting out. And how it is emitting out? We know sigma T to the power 4. Okay, for Earth, now if you consider Earth to be a single point, okay, and consider it to be a black body, so let's define that temperature as TE, temperature of Earth. Okay, so this is Sun, this is Earth. This amount of energy basically comes to Earth. Okay, 1365 watt per meter square. Some of it gets reflected, and because of Earth's temperature, it radiates out the long wave radiation, right? But let's see how you can basically get the solar constant. So that 1365 watt per meter square is called solar constant, right? And how do you get that? So sun is emitting, sun has a temperature, which we know to a very, precise value, as Professor J.S. used to tell me. So this is the temperature of sun. And so the amount of energy it is emitting is 4 pi r square sun sigma T sun to the power 4, right? And now you have to consider, so energy goes out, how it decreases with distance by it is proportional to 1 by r square. Okay, so what you have to do then, you have to basically use this distance, the mean Earth sun distance you can use to calculate that. So 4 pi MSE square, right? The mean Earth sun distance. So that will give you, if you plug this number here, you will get the solar constant. So now again coming back to energy balance. So the energy balance then will look like S pi Re square minus alpha S pi Re square and the amount that is emitted by Earth, right? So now if you solve for TE, what is the value of TE you will get? Can you do that for me? Huh? What? No, just quickly do it. What did you say? Minus? Yeah, cool. So it is minus 18 degree. So, but I was expecting something here from you guys, that you will ask something. So what is going on here? See here what we did. So in the case of sun, we are doing this, okay, right? But can you tell me, because you did not ask, I will ask you then, maybe you know, so you didn't ask. So why you have this S pi RE square? No, raise your hand and then speak up. So only one cross section of Earth at a given time is exposed to sun, right? So you don't have that 4, you have to multiply it by pi RE square. And that's how you get this balance. Anyway, so the value of TE, so you solve this, you will end up with something like this. This is a very simple equation, okay? But it all starts from here. I'll show you in a while at how important it is, although it is a very simple thing, which Fourier did in 1827. So now, as he said, TE is 255 Kelvin for alpha 0.29, okay, which we got from that particular energy budget diagram, right? The energy flow diagram. So now, but the present surface temperature is 289 Kelvin. So this difference represents greenhouse effect, as Yash was telling me. So this temperature is because of the greenhouse effect. But as such, greenhouse effect is basically this thing, what 150 watt per meter square, okay? You remember, this is slight, small difference between this particular thing. The temperature change, the 34 degree Kelvin is because of greenhouse effect, okay? And the amount of energy is this one. So here I show you the black body curves for sun and earth. So they have scaled up, so they look very close to each other, but this will be really here. And why you have greenhouse effect? Because you have the major gases, they don't absorb, but there are minor gases like H2O, CO2, methane, nitrogen oxide. They have strong absorption bands in the electromagnetic spectrum of sun as well as earth. But in our simple model, we had TE, temperature of earth, right? Which is 255 Kelvin, not 289. So how do you model that? How do you get to T6? TS. So the simple thing would be, let's add one layer, which we can call as atmosphere. So let's add one layer atmosphere to this thing and look at it. But before going there, I want you to solve this particular thing. Please take pen and paper and work on this. Say small black body satellite is orbiting the Earth at a distance far enough away so that the flux density of Earth radiation is negligible compared to that of the solar radiation. And suppose that the satellite suddenly passes into Earth's shadow. It is behind Earth and the sun doesn't see it. I mean, it doesn't see the sun basically. So at what rate will it initially cool? And the characteristics of the satellite has been given. So whatever we have done until now, you can use that to get this thing. And of course, a bit of thermodynamics, tiny bit of that. I'll give you a minute. It should not take more than a minute or two. So it goes behind the Earth, right? So the satellite doesn't see anything from the sun. So the albedo there is no albedo. Alpha you can consider to be 0, right? Because it is not. Anyway, so work on this. The answer should be 15.5 Kelvin per hour. Okay, this is the rate at which it will initially cool. Please write this down and work on this. Okay, I'll ask in my tomorrow's lecture. How did you do it? Okay, moving ahead. So let's take a peek at the atmosphere, quick peek, because we were talking about greenhouse gases and the concentration of different, constituents of the atmosphere. It has low battery, I guess. So, and the structure of the atmosphere looks like this. I have taken from Wallace and Hobbes. So here you see in the troposphere, the temperature decreases at a faster rate. At a fast rate. Yeah, I cannot relate it. So what is the typical way temperature decreases in Earth's atmosphere? Anyone knows that? So that is the when the atmosphere is dry. Yeah, when the atmosphere is dry, let's yeah, so that is a typical number. Okay. So anyway, look at the constituents. So when we talk about climate system and climate change and stuffs like that, we are mostly worried about troposphere and our neighbor stratosphere. Okay, we consider ourselves and our neighbor. So for us, mostly we deal with troposphere and stratosphere. And so look at the constituents and their values, and you can see water vapor is only 0 to 5%. And carbon dioxide has 380 ppm. But why 380 ppm? What is the current concentration of carbon dioxide in the atmosphere? Huh? But why it is something like that? Because the book was a little old, So for Mike Wallace, it was 2005 or maybe sometime like that. So that's why it is low. So methane, which is another very important greenhouse gas, it's a very highly potent greenhouse gas. The concentration was low, but now it is much more. And this shows. But the thing is, I would, other than that problem, I would want you to calculate this 380 ppm or 420 ppm that he was telling in kgs or in gigatons of carbon, so that you know how much carbon we are emitting. And not CO2. Okay, so do this as well. And the other next question is, a lot of people have worked on COVID-19 data and all. So does COVID-19 pandemic has an influence on the rise in CO2 concentration? Does it have? So please, yeah, Yash, tell me. But do you think the CO2 concentration has dropped? It has decreased. It is only the rate of increase of CO2 concentration has slightly dipped. I had that plot as well, but I just because of time, and I did not want to rush things, so I did not put those things here. But anyway, I'll show you here. So please, so if someone is not aware that what is actually happening, please go to Killing's website. Okay, and look at the values. Okay, look at the graph, what has actually happened. And don't believe in what people have said or what medias have said. Look at it for yourself, because data is there. You just have to plot it. Okay. You just plot it and you'll see that there is very, very minor dip. And that is not there in this long term. That dip you cannot see here. Okay, so this is the carbon dioxide concentration at Mauna Loa Observatory. I took it from, of course, this website. So this is the same website I was talking about. So, and it shows how it has increased since, so they started in 1958, how it has increased since then. So now if you plot the same thing on a longer time scale, this will be very steep, okay? So now the next question is, why do you see this oscillation? Who can answer me this? Please raise your hand. Yes, Resh. Okay. So you're saying the dip is because of the northern hemisphere biological activities and also vegetation and all. Okay. So yeah, so it is because of the vegetation biological activities in the northern hemisphere, because of which you see this dip. So now coming back to the balance again, it looks very simple, but what you can do, you can put a constant here. proportionality constant here, and you can change this TE to TS. You can do that, okay? To make it more, like connected to TS, although it's a simple 0D model. So now, before going into that one layer atmosphere that I promised, let's see how each of this thing looks like, S by 4. So what I have done, I have used this, I have run this MPI ESM in the historical period from 1850 until 2017. And I took from 2004 to 2015, this period, okay, and calculated this S by 4. And I'm showing you here in the global map. So I've done using Python. So you can do this in Python. You can try doing that, okay. I can give you data. So this looks like this. So here you see the bar. So yellow is very lot of energy. So what is the first thing that you see? Where do you get more energy? Huh? Yeah, so in the tropics, right? Around the equator. Not exactly on the equator, around the equator in the tropics. And what is happening here? Why it is dark, I mean red and all? Red, orange. Speak up, yeah, raise your hand and speak up, yeah? Yeah, so it is because of the period. So I was trying to show you such that both have equal amount of red on both the poles, but it didn't happen. So because it is March, April, May, you still have less solar radiation going into the southern hemisphere because it is closing towards the northern hemisphere summer. And now you see the number. This is a full Earth system model, okay? It's a full Earth system model, and see the number. This is 338, very close to the 340 watt per meter square, which we have seen using the simple balance energy balance model. So now let's look at S by 4 alpha. This is the albedo of the planet. Now see the color bar and then look at it. And now you have to tell me, why do you see this dark patches here and light patches here? Huh? Yeah, you tell me first. Yes. No. You have more sun, you have ice and all, so you have more reflection here. Okay, so more reflection, I mean more energy is going out. This is the out energy that is going out. Okay, I mean going out of the system. And yeah, you're saying something? Okay. So one thing you all are missing. So this is a full Earth system model. Something is there, right? Clouds. Cloud is also there. So that will also change the albedo, right? So wherever you have more clouds, more low-level clouds, very bright clouds, they will reflect. So that's why you see this southern hemisphere is known to, southern ocean is known to have a lot of clouds. So you see it is slightly more energy is going reflected back. And that's why I also have this total cloud cover from the model. And you can see southern ocean has a lot of clouds, but now the solar radiation was also less because it is March, April, May. So only a small amount of energy is basically getting reflected back. And this is in total S by 4, 1 minus alpha. Okay. And you can see the mean is 238.5 watt per meter square. We saw it was something like what? 240, right? In the global mean, the energy flow diagram. So which is again very close, 1.5. But 1.5 is again a very large number. But again, it is a model. So there are some other limitations of the model. And it's a very averaged value. So, so this represents sigma T to the power 4, or you can say epsilon sigma Ts to the power 4, okay? This pattern. So this is how Earth radiates back to the space. Okay. So where it is more, it is in the tropics. So which means tropics are hotter, right? Warmer than the poles, right? So simple from the energy balance, you can talk about the temperature. And the mean difference, well, so this is 237 that is getting radiated back, at least in this model for this period. Okay. and the difference is 1.5 watt per meter square, and it's a huge number, and that's why there is a mean warming as well. I don't think I have TS plot. I should have done that. Okay. Okay. So now I have now shown you, although it's a simple energy balance model, you can see how important these are. I have shown you each of these components, each of these things. So I have taken this from Pixoto and Oat, 1991, and this shows you the zonal mean profiles of this. So this is the around the year, this is the thing, this is the June, this is the December, January, February, and all. And this is the albedo, the reflected watt per meter square in watt per meter square. Okay. And this is the albedo. Okay, so that was the reflected, which is what? S by 4 alpha, S by 4 1 minus alpha. And this is the absorbed one, and this is the net radiation. This is northern hemisphere, southern hemisphere. So what do you see here in a net radiation? Yeah, you see that. So the thing is, now the amount of energy that is that sun earth receives, it looks something like this. Okay, and the earth emits radiation back to space, it looks something like this. So what does the system has to? Everyone wants to be in peace, right? After the whole day's work, you want to go to your room, take your time, have a nice nap, right? So that is the nature of everything. So what it will do now? So it will have dynamics and all to distribute this energy, the excess energy that is there in the tropics. And that's where all these dynamics and everything comes into picture, and you have to model it. Okay, so here I have also shown you how this energy is gets transported. Well, I wanted you to guess, but the more amount of energy is transported by the atmosphere and less by the ocean. So this one is ocean, this one is and this one is the net, the dark black line. So this is the amount of energy this is how the energy is transported from the poles towards from the equator towards the poles, from the tropics towards the poles. We have time. So now coming to the one layer atmosphere. So one layer atmosphere, what you can do, you have this basic thing that we have done already, and you can write down the surface energy balance for the surface. I mean, the energy balance for the surface. So which will look like this. And you can solve this to get TS. So now if you plot, if you plug in the values of S alpha, which is 0.3 or 0.29, whatever you want to consider, and solve this, you will get TS some number. Can you see what is that number? Do we have time? So in this case, what we have considered, we can say that this one layer atmosphere is a slab of perfect greenhouse gas, which is transparent to the solar radiation, the short wave, but it is a black body absorber in the infrared. Okay, that is how I have revised this. And you can write this energy balance. So you will get a number which is not close to 288 when you solve this. Okay. So what you can do then, let's add one more layer. What happens then? Does it improve? So let's add two layers now. You add one more layer here and one top of the atmosphere layer. So now you can, if you do this, you can write simple. It is the net balance that we have done already. For the surface, the solar radiation is coming, which is S by 4 1 minus alpha. Sigma T1 to the power 4 is also coming from this first layer. Okay, and the surface is emitting some long wave. So minus sigma Ts to the power 4. So this is the balance for the surface. Now what is the balance for the T1? So T1 is 2 sigma T1 to the power 4. T is this layer is again radiating it to T1. So it's this one. And again, it is receiving from the surface. So this one. So now if you solve all this, it will get an expression something like this. Okay, I've done it very quickly, but this should be fine. So this should be the temperature. But if you haven't, I see that you haven't basically calculated the value of TS in the first case. Huh? Cool. So can you do it quickly for this? So what do you guess? It will be more or less compared to what he has calculated, 382. So it is more. So adding more layer, adding more slabs of greenhouse gases is not helping. It is, yeah. So it is increasing, right? The temperature 302 and 335. Yeah. Okay. So what happens if you have n layers then? Please find. So this is the fourth question that I'm going to ask you tomorrow. You have to find this out. Okay. For an n layer system, what will be the expression? And for let's say 15 layers, what will be the value of TS? Okay, not 15 layers, 50 layers. Very fine, lot of layers. So you are really making this your model very complicated. So this is one case. The other case is that let's see that let's not make the whole layer to be a perfect greenhouse gas. Okay, let's make it partially absorbing. So when you do that, you have something like this, that solar radiation is coming, okay, only a fraction of it goes to space. So this is going to space from the surface, and the other layer has some fraction of energy, a fraction which is absorbing, okay, energy that is coming from the surface. So now if you go for this, you have slightly better way of modeling it. So this is how you build from a simple model. You add layers. Okay, no, not perfect greenhouse gases. Let's make it partially absorbing. If you do this, now you will get, if you plug in the numbers, alpha's value and all, you will get a very nice value for TS. But again, but you don't know the value of F, how much is getting basically, what is the fraction of energy gets absorbed. So what you can do, you can put TS to be 288, alpha to be 0.3, and you can calculate the value of F. So for our atmosphere, the typical value is something like 0.8. The F value is 0.8. Okay. And how TS and TA are related? How they are related? What do you see here? TS is, this makes sure that TS is always greater than TA, right? So all this while, we were looking into the model, right? But it was always radiation, right? We were talking about radiation. But if you remember, when I showed you the energy flow of the climate system, we also had latent heat, right? LH, and this curve, rate curve, which was going up, and there was rain, and all those things were also there. So we haven't considered that in our models. So what happens if we consider that? We will improve our model, right? And we should be getting a better value for TS, because our aim is to find TS, and TS is what is climate, right? TS is the primary variable which drives all the other variables. So we have to know TS. So we have to predict TS. So you have to build the model in that way. So the next step is to get into the radiative-convective equilibrium. Okay. So all this while we were talking about radiative equilibrium, but the next thing would be to add radiative-convective equilibrium. So before all, I was talking about Fourier, and I was talking about Arrhenius. It was mostly, radiative equilibrium they were talking about. But the guy who basically revolutionized this idea, so it was Suyukuro Manabe and this paper, Manabe and Strickler, 1964. Okay, and that's why he got the Nobel Prize for this work. This is not working. So this battery has to be changed. So these are the two papers which are very, very useful, very important, and I would urge you. I'll give you some. I'll show you some evidences that why you must read this particular paper, Manabe and Strickler. So this was for the Nobel Prize was to Manabe, Hasselmann, which Hasselmann, Ashwin talked about him yesterday. The same paper he showed Hasselmann 1976, because of which he got this prize. Okay, for the physical modeling of Earth's climate, quantifying variability, reliably predicting global warming. Okay, so it was basically the single model radiative-convective equilibrium that Madhava has produced, and he has actually made the model, go forward, march forward in time and calculate the temperature values. I'm going to show you some evidences. I don't, of course, in this lecture. So anyway, before going into that, so let's read this, okay, carefully, patiently. The aim of Manabe's research, like that of Arrhenius, around 70 years earlier, was to understand how increased levels of carbon dioxide can cause increased temperatures. So again, his aim was to find temperature and relationship to greenhouse gases. And for that, he wanted to make a model. However, while Arrhenius has focused on radiation balance, as we were talking about, in 1960s, Manabe led work on the development of physical models to incorporate the vertical transport of air masses due to convection, as well as the latent heat of water vapor. Okay, so this is what was a quantum jump in the knowledge, So and even it was a single column model. To make this calculation manageable, he chose to reduce the model to one dimension and a vertical column of 40 kilometers up into the atmosphere. And even so, it took hundreds of valuable computing hours. It was in Princeton to test the model by varying levels of gases in the atmosphere. And he saw that the temperature rise for a double CO2 is 2 degrees. But Arrhenius predicted 5 to 6. So there is a huge difference. Just adding convection, that's the difference. Okay. Let's go ahead. So here so it is the same thing that I was. So he has basically this cold air coming in, hot air is going out, and he has also considered the radiation, both of them. You can read that later in the. So now I'll show you how the pure radiative equilibrium temperature profile and the convection, when you add convection, they look like. So this is the pure radiative equilibrium temperature profile, this one, okay. You can see it is very, what you call not steep, less steep, whereas this is the dry adiabatic, which someone has talked about 9.8 something. And this is the actual one, which again, some people, Shreyas and others have talked about, right? So they look like this. Now again, the next question is here. Again, this has been taken from Manabe and Wetherell's this paper 1967. Now, can you tell me? So he has basically done experiments with different CO2 levels. Now tell me which one is a higher CO2 level profile, temperature profile? The blue one, the black one, or the red one? You have to also be careful about the profile here, okay? The temperature differences here. So it is basically the red one is the right answer, but you see in the stratosphere, it is much colder than the others. Okay, so this is another, a lot of people worked into this, why the stratosphere cools down when you increase greenhouse gases. Okay, please read on this or think about this, okay? Altitude, and x-axis is temperature. Altitude. With height, how the temperature is changing, okay? Same as here. Here it is pressure, on this axis they have given altitude. So now just to motivate you more to read that paper, Manabe and Strickler, okay? So he has used this simple temperature to march in time, okay? He has used a critical lapse rate, and he has considered the critical lapse rate to be 6.5. He said that I have no other way to basically prove why 6.5. This is what is observed, so I have used that as the critical lapse rate, okay? And there is, so he has made that to be the threshold. And then see, he has solved all this and he made his computer model to run, and from 0 day until this is, I guess, 240 days, he has basically shown how the temperature profile has evolved. And you see, this was a straight line, and how it has. So initially it is more like a radiative equilibrium only. Convection was not in the first 10 days, probably it did not much because but you can always go and read the paper again. I read this paper during my PhD's master period. So you can see this, and more on this, he has also included radiative equilibrium. He has started with that model. He has developed, like he has included the convective adjustment. He has then included the atmospheric absorbers. He has included the clouds in his model, and you can see how he has done it. Okay, so that will give you an idea that how you can actually work on such simple models and build on them. So then he has included the stratospheric water vapor, and then he looked into not just vertical but how latitudinally it will vary. So here I'll show you the rate of temperature change for different greenhouse gases or the gases that atmospheric observer he has considered. They look like this. And this is in equilibrium with the clouds. Okay, you can please go ahead and look on this paper. So now all this while it was radiative equilibrium, radiative-convective equilibrium, and now I'll give you a sense of time how you can So again, this should be a very simple model, but the whole concept of climate feedback, climate change, climate sensitivity comes from here. Okay, so let's say you have the atmosphere, and you suddenly you see a step function change the composition of the atmosphere. So how the planet will respond? It is something like this. So it has it has inertia, right? So it will not jump like the forcing. So it will take its own time, right? It is increasing, and there will be a point when it is almost stabilizing. There is no further increase. But what happens at the top of the atmosphere? We have to see the top of the atmosphere because we are considering the planetary energy balance. So in that case, you have to see this and this shaded region. So there is a dip in the forcing, the amount of energy that is going out, because suddenly you are increasing the greenhouse gases. So for momentarily, nothing escapes. And then it starts increasing because of the increase in temperature. The amount of energy going out in long wave also increases. And this shaded region is the energy that is heating up the earth. Okay. And this is responsible for climate change. Okay. So now you can model this heat capacity of the system, global heat capacity. T is the temperature of the planet, or the surface temperature, you can say. F is the forcing. And when we say forcing, we always mean radiative forcing. Okay. Radiation balance at the top of the atmosphere. So this F is basically radiative forcing. Okay. And this can come from CO2, ozone, land use change, aerosols, anything. Okay. And this lambda that you see here is the climate feedback. And this delta T is the temperature change or the climate change that we are talking about. By the way, this is D delta T. Okay. This is D delta T. And now, so the primary thing here is that you can calculate the forcing, although it is tough, but you can somehow know this. Okay. You can again measure the heat content of the planet by, let's say, how much heat content is there. There are ways to do that. But how do you get this, the lambda? As Aman was also talking about the yesterday, right, in his talk. So you can use simple y equal to mx plus c. This is a simple y equal to mx plus c equation, linear equation. But the trouble in climate science, which is the central problem, is to find the value of m, which is lambda here. Okay, the whole climate science is about this, finding the right lambda. If you find the correct lambda, you can project the future climate very easily, right? Because you give the forcing, you know lambda, you can get delta T. But you don't know lambda, that is the thing. Okay, the uncertainty is very high. And that's why you see it is fine, and the moment it starts projecting, it spreads out. Okay. And how do you get lambda? What you could do here, you have to take the help of GCMs when satellites were not there, because you don't know how much energy is basically radiating out from the planet. So what you could do, you can plot the change in surface temperature on x-axis, change in the net radiative flux at TO, which is the energy content that is heating up the earth, the shaded region. If you plot them, these are the annual mean values. This is a very simple, cartoon of that. the slope of this is basically the lambda, the m. Okay, but the problem is this slope changes. Okay, if you apply a different forcing, this slope is different for CO2, this slope is different for methane, this slopes changes over time. Okay, I'll show you some example. So it bends. So then what value of lambda you are going to use, where you are going to take a slope. Okay. So again, very quickly, so this is the delta T, that is how defined, and there is a very, like everyone talks about the equilibrium climate sensitivity. So it is nothing but this delta T, but this forcing is only because of doubling of CO2. So now you can relate why people always use doubling of CO2, because initially Arrhenius has started with that. Okay, and later on many people like Manabe has looked into double CO2. So that's why it became a standard. So they define the equilibrium climate sensitivity as a parameter, which is basically the ratio of F2x CO2 divided by the lambda. But you don't know lambda, you have an uncertainty. So you have an uncertainty on the ECS. And that is what the central problem in climate science is, to estimate this ECS. Or there is another sensitivity called TCR. So now lambda is basically a sum of various factors. The Planck feedback, okay, this is the total feedback, Planck feedback, water vapor feedback, lapse rate feedback, surface albedo, clouds, and all. And you can get an idea if you differentiate this equation with respect to TS. Please do that, and you can get an idea of Planck feedback, albedo feedback, and the lapse rate, clouds, and all the other. Now the cloud is also added there, but also in the albedo. I can show you tomorrow. So this is from the present IPCC report. This is the net feedback. So you can see how wide it is. I guess I was talking to Sijil, Shreyas, and Giri that because of this spread in the lambda, the ECS is so wide that you cannot project the future climate change. And how different feedback factors has contributed to this net, you can see from here. So Planck feedback is the only one which is very accurately, you can measure it, you can estimate it. So that's why the thing is very small. And these values are from AR6. This is from only models which has participated in this CB5, the last generation of models. And this is the latest generation of global climate models. And the spatial structure of the feedbacks look like this, okay? But I guess I am over time, so I'll stop here. Thank you. So I'll continue, I'll build from here on the feedbacks and the models, okay? Thank you very much.
Thanks, Angshuman. Do we have questions from Angshuman?
Yeah, so regarding the climate feedback slide, if you could go there. Yeah, so the next, so here we can see that the climate feedback is like, the climate feedback term is like linear with respect to the temperature change. So could we expect non-linear terms as well? Like,
you can add, you can add.
And is it hard to determine the uncertainty?
Yes. So Pierre Humbert has taken this up some time back, but again, his PhD student, he has added another factor. So it is basically a Taylor series. So you can add something else plus beta delta T square. So it basically improves your model again, but again, it's a challenge, to calculate the beta.
Right. But this is a good enough.
But this is what the whole climate science community is looking into. Okay. And to calculate the lambda. And I'll show you in the next lecture how this has different implications, the uncertainty in lambda.
Any other questions?
Yeah.
You have a question? Yeah.
Just showed the models, those three models. You showed the 3 generations of models.
Okay, radiative, equilibrium.
So, there was no visible improvement in the uncertainty or?
No, that is like we have seen, right? You have one layer, you have 302 Kelvin, he said. If you increase one more layer, if you add one more layer, it increases the temperature value. So there is no improvement. You wanted something like 288, right, for your model to predict, at least to give. They are all diagnostic. Now here, this model is a prognostic. You add time to it. But again, Manabe, what he has done, he has developed a single column model, and he has also masked over time. So he has made the diagnostic model into a prognostic one. And this is how he has done. So I, of course, I cannot, cover all this because, yeah, but I wanted to motivate you to read all this and know about these models. We can talk more if you have further things to ask. Yeah, Nihal.
Angshuman, thank you
Yeah.
for the talk, and it was very nice. Out of curiosity, I'm asking, like 3/4 of the Earth is covered by ocean,
Yeah.
right? And you have long wave cooling as well as latent cooling.
Yeah.
And when you do that equation CPDT, what CP you are taking is for the whole Earth?
Yes, that is the thing. Very good question. So I missed this point. So this global heat capacity is primarily in this equation is primarily the ocean, what he has pointed out. And also, if you remember yesterday in Ashwin's lecture, Vishal pointed out the heat capacity would be really huge, right? So it is really huge. So now again on that, I will show you another model tomorrow. So again on that, if you just consider the mixed layer, I'll show you, I will give you a value for C. So indeed, only the ocean we take care, because even if you see the IPCC's that energy flow diagram, they show the whole heat content heat is going inside ocean. That is how it is represented, and that is the only way, right? Because atmosphere has very low heat capacity. It can be like, that's why atmosphere is like fast time scale weather kind of thing.
And what about the surface fluxes that the ocean exchanges with the atmosphere? That part?
Yeah, so that comes here in the lambda. That comes here in the lambda. You mean the latent heat and sensible heat, right? So mainly mainly we consider latent heat flux for the simple calculations, but because it is much higher than the sensible heat flux. Yeah. Basically, Niha, there is a way to. I showed you that IPCC. I have tried to see, can we get those values from this simple model? I have tried that, but it is, you have to make several assumptions and you have to know a priori some values to calculate particularly the sensible heat flux. You can calculate the latent heat by just multiplying the latent heat of vaporization with the precipitation change that has happened, which you can predict through delta T. That gives you a very nice number, close to 83 watt per meter square.
Yeah. It's very nice talk. I'm also learning this thing. So one thing is that if there's a lot of changes is happened because of the ocean mixed layer, so then mixed layer parameterization is also playing a very important role, like the mixing inside. So
yes, definitely. So currently, recently, I will partly show that maybe in few slides. So there is this new concept of pattern effect. So pattern effect is how the radiative feedbacks is dependent on the surface temperature. The pattern of planetary warming. So it is mainly the ocean, how the ocean temperature is distributed. So there, what we have, our aim was to estimate lambda and ECS. That is fine, but the overall question is that why this particular pattern that we see is why that is happening. The models are not getting. So the whole concept of pattern effect came from this. So 2013, Otto et al. Used the historical period 1850 to 2010, I guess. She wrote that paper 2010. And she used that period and constrained the equilibrium climate sensitivity. And she told the value would be between 2 to 3 degrees centigrade. Okay, but all the GCMs then were showing that it will be 4 to 5 Kelvin, 4 to 5 degrees centigrade. And several people looked into it and they figured out that we are not looking into the spatial pattern. As you said, we are not basically looking into the mixed layer part of the thing.
So it is just like a one dimension.
So we are considering the entire ocean to be one, right?
It doesn't have a advection.
No spatial, nothing. So that's why. So now how do you, but our aim is to estimate ECS, and this is the only way to calculate ECS. So how do you do that? So I have worked a bit on that. I'll show you some of that tomorrow. Very interesting question. Thank you.
Any other questions? Okay, if not, we'll thank Angshuman once more and we'll break for lunch.
Yeah.
Thank you.